Welcome back again. This is Larry Benko, W0QE. In this video, we'll explore what happens to the frequency response of a filter that is operated with different source and load impedances from what it was designed for. Previously, I have shown how to calculate possible increases in voltage and current on components, and I did that in video number 51. Filters are designed for a specific source and load impedance, and when operated with different source and load impedances, it's reasonable to assume that the frequency response will not remain constant. Nearly all filters, and especially those that directly connect to an antenna, will see varying impedances versus frequency. Prior to SimSmith, doing some of these types of analyses were laborious, and I didn't enjoy doing these types of calculations. For the video, I'm using a beta version of SimSmith 16.3, but I'm not using any features that are not already in version 16.2 or 16.1. Once again, we'll see how easy SimSmith can do these kind of calculations. Let's start with a SimSmith circuit, which has two filters that I've built. And the two filters are the same filter. One is done with an inductor input, and one is done with a capacitor input. They're 3-pole filters. They're 10 megahertz Chebyshev filters with about 1/10 of a dB. I don't remember, maybe 1/8 of a dB ripple. But they're both identical. They should have the same performance exactly. I have two circuits, two generators. This generator here is cloned here. This load impedance here is cloned there, and we're good to go. I have a D block here whose sole purpose is to take whatever value is in here and put it in Z0. So I can change both the source and the load impedance at the same time, just for show. Other than that, it's pretty straightforward. So let's look what happens at whatever frequency you want to. I've got the markers set here at 30 megahertz right now, and both of them have almost exactly the same loss. Now I built these with components that are real values. So two inductors will have more loss than a circuit with one inductor. And we see that a little bit up here where you can just barely see. Let's go up and look at it. We can see here that the pink curve is a little bit more lossy than the black curve. The pink curve is the LCL version. And I just named the load generator block and the load block this, so I knew which ones were which. But the one with two inductors is a little bit more lossy, but that's pretty negligible to say the least. So now let's look what happens if we change from 50 ohms, which is how it was designed, and let's go up to, say, 60 ohms. At 60 ohms, we see the black filter, which is down here, the filter with the two capacitors. It has better response at 10 megahertz and a steeper skirt than the purple one or the pink one, which is the one with two inductors. And if we think about that for a minute, as the impedance of the source and the load rise, the effect of the capacitors will be more pronounced. The shunt capacitors will be more pronounced than the effect of the series inductors. And likewise, if we drop this impedance down to 50, they're back even again. But now we go to 40, exactly the opposite has happened. The two inductor filter has the better response, both at 10 megahertz and throughout the passband, with the exception of a little bit here in the passband. If you were to use the filter here, you might care about that a little bit, although this loss isn't really that much. It's half a dB. But what we see is if we continue this down to, say, 10 ohms or something, the filter's response is pretty bad, and the two capacitor filter is really bad. Effectively, by the time we get down to values like, say, 10 ohms here, the effect of the two capacitors is pretty much nil, and all we have is just a series inductor. Likewise, if we go up, we see the same effect taking place with the two inductor filter, where it starts looking really bad, and the two capacitor filter is better. I mean, of course, it doesn't look great either, but this is pretty typical. We can see this also in SWR. If we plot the SWR of both filters, we see they almost line up. They don't quite line up here because the fact that the green one, which is the one with two inductors, has a little more loss in it than the one with one inductor. So we see just a little bit better SWR, but it's pretty negligible. But watch what happens to the SWR as we change the impedance. As we go up here, we see the SWR rising on the blue curve. The blue curve is the capacitor input filter, and it's the one with the better response. And that just goes to show that these types of filters get their attenuation solely from mismatch loss. They have no components within the filter that are capable of consuming anything but negligible power. Consequently, if we have some power that needs to be attenuated, it's got to go somewhere, and it goes by the wayside via mismatch loss. So the SWR, the filter in the stop band, gets very, very high. You get pretty much 100% of the signal reflected back to the source. And the same thing happens on the output too. It's the wrong impedance for driving the output, so there's not very much power transfer there. But this is the kind of thing you see all the time in filters. And people ask a lot of times, I've been to Hamfest and stuff where I see 75 ohm filters available. And the question is, if I had a filter that was made for 50 ohms, could I use it at 75? And the answer is, well, if it's a 2 capacitor filter, probably it's okay. What about a 75 ohm filter used at 50 ohms? Well, it's going to be on the opposite side, so it would be like using it at a lower value, lower impedance than we set it spec for, and we'd be better off if we could find one that had 2 inductors and 1 capacitor in it. Or you just basically say you don't care and realize that the fact that the frequency response isn't quite right. Let's go to another example to show this a little bit better, I think. And for a second example, let's look at this filter. I have a 5-pole Chebyshev filter with a 1/10 of a dB ripple. And again, I have 2 circuits working here. The first circuit, we're going to always have a 50 ohm load and always have a 50 ohm source. We have a 50 ohm source here. We clone the generator here. So we have a 50 ohm source here, 50 ohm load. This filter is operating as it was designed. This filter, which is an identical filter, is in a circuit where we're driving it with the right source impedance. Now, we could drive with a different source impedance and the right load impedance. It wouldn't make any difference. You'll still see the same kind of thing. But I chose to make the load impedance variable here. It's a 2-to-1 SWR, and I have a transmission line delay in here. The transmission line delay is done with a D block, and it's calculated such that no matter what frequency I'm at, I have the same amount of phase delay through the transmission line. And we calculate that by 984.2 is for feet. That's lambda in feet divided by megahertz. That gives you the wavelength for the frequency you're at times the delay in degrees over 360. And if we look at that down on the Smith chart, what we see is 10, 20, 30, and 50 megahertz are all at 100 plus J0 when the delay is set to 0. If I start moving the delay up, all of them move at the same time. And there's really no reason to have to do this. I just wanted to make sure that if I used the regular piece of transmission line, I'd varied its length in feet. As you get up higher in frequency, you can start skipping around, and if you get in sync with what a wavelength is at the frequency you're at, you don't get to see all the different phases for that frequency of impedance. So I did it this way, and with this simple calculation. And what we get here is we get a graph now. We plot the solid black line is a plot. And this brings up another point. In version 16, the plot command has gone from a small p to a large P. It's a little more rigorous than it used to be, separating the fields now instead of just a space or commas. And it's documented in the manual, and the manual's gotten a lot better too. So take a look at it. The manual with version 16.3, which should be out soon, is also searchable. Clickable. If you click on the index, you go to the page directly, which is a really nice improvement. So I plot down here second. I want to plot this one second, so the black line's on top. So I plot the dots first. The dots are for this filter, and so plotting dots of the power into the load here at LG1, and then when I follow it up with plot a line, which is the black line, it's stroke of 5, so its width is 5, and I plot the power at the load L here. And this is what I get. So if we look at the 30 megahertz ambiguity here with 41.6 to 47.6, it's a 6 dB difference in ambiguity for the loss at 30 megahertz, which is 3 times the cutoff frequency. If I increase this so that my SWR gets higher and higher and higher and higher, let's go up here to say like 1,000 ohms. And 1,000 ohms represents a 20 to 1 SWR. Now, I'm starting to see some issues here, and part of that's the problem. I don't have enough points here. Let me add some more points. We're good to go with there. But pretty soon I'm going to exceed the maximum sweep size I can do without doing a full sweep. There's a full sweep now. So now with a 20 to 1 SWR, we see at 30 megahertz a difference of 31.7 to 57.6. That's 15.5 dB, if I did that math right. So it's getting larger. If we go up to say 2,000 ohms, it gets even larger yet. 28.8 to 60.5. Okay, so it's over 30 dB of difference with that kind of an impedance, with that kind of a SWR, and that's not an unreasonable SWR for an antenna to give you if it's at a certain frequency where it's not resonant or anything. So you have to be careful when you build a filter and what kind of circuit you put it in. And that was the whole point of doing this. Of course, if I put I wouldn't have a 2K load down here at 10 megahertz that have something closer to the right frequency, or excuse me, the right impedance at 10 megahertz. This shows the 10 megahertz response being down over 10 dB, which is the mismatch loss from this kind of a load. But I wouldn't have that. What I would have is I would have impedances up here that would be pretty close to what I designed the filter for. And then out here they would start to get increasingly bad in terms of what the filter was designed for. And consequently, that could give me better attenuation or it could give me worse attenuation. And you really never know that ahead of time. Of course, if you know your load that you're going to be operating into, and you took a network analyzer and you measured your load, you'd replace this circuit and this little calculation stuff here with just a scanned file right here. And you would know exactly how your filter would perform. So if you're capable of having a captive audience, so you know what the filter is going to be faced with, you don't have to do any of this. But this is just kind of, the point I'm trying to make is, if you're surprised that there's a 30 dB variation at 3 times the cutoff frequency with wild SWRs, don't be. That's kind of the way things work. Hope you find this video interesting. SimSmith does these kind of analyses very, very well, and it's super easy to do in SimSmith. And this is just another one of the cool things about SimSmith. If you like this, give me a thumbs up and tell me you like it. If you don't like it, let me know why you didn't like it. Appreciate it. Talk to you later.